Alright, time for another DraftPhysics.com, debatephysics.com also. Video presentation. Another Sabine Hossenfelder video, this time on energy. And I think I'll, keep pursuing, see where I can find videos where she's talking about something real, not the abstract, forky symbol kind of crap and whatnot. And here she's talking, I can't get more elemental than energy in terms of the subject of physics. It's, to me anyway, it is physics. There's no other conversation about anything other than this transferring of energy from one form. Okay, it's always the same energy, frankly, the substance is the same. And you're just talking about how it pours from one thing to another, in a sense. Well, I'll draw some of that and explain. And so the real point is the kinetic energy, the use of the term for energy. So they'll often put the word kinetic in front of energy, and that associates with a formula that they concocted out of nothing, no experimental reason to do it. And where they say energy equals not mass times velocity, but 1/2 the mass times the velocity squared. And to solidify that nonsense, they perverted Newton's gravitational formula into 9.8 meters per second squared for no good reason. It's 9.8 meters per second, 1 second, per 1 second. Okay, so there's no squaring of seconds. Anyway, it's not per second, doesn't mean second squared, because it's per 1 second, per 1 second. Anyway, yeah, that's probably enough of a premise. So maybe I'll explain what energy is first, and then we'll play the silly conversation. And it wasn't even, frankly, it was so thin and weak, and it was a grammar school description of energy. I think it's a few years ago, 3 years ago, before she became famous, rich and famous on YouTube. And you gotta say, I think she used to make her own clothes. I mean, I think she thought this looked good. Not that, I don't have any right to talk about style because I don't have any. But if you're going to try to be stylish, then somebody can critique it. And yeah, what the hell what were you thinking? Why not just draw circles? I mean, it just, there's no point. All right, anyway, what the hell is wrong with this camera position? It's just off somehow. Well, it always should be a little bit off. Because, frankly, I'm tired of the whole thing. It's just so tedious talking to humans. It just sucks all the will to live right out of you. All right. Yeah, like I had any to start with. Anyway, so energy is movement in the universe. The simple argument is something has to be moving, then you say it has energy. And if it's not moving, that is, it's not relatively moving or absolutely moving, it's not going to be able to create a conflict with something else. So their energy is only acknowledged as an event when there is going to be a transfer, when two things are going to collide and some kind of event is going to take place. That's going to mean there's going to be a transfer of identity. And the idea is the stuff has to be conserved. Not necessarily the direction, but the stuff moving. There has to be the same amount of stuff moving before and after. That's conservation. And that the motion never stops in the universe. So this is a Descartesian idea. Where Descartes basically said the universe was pushed into motion by God, and the motion is just moving through the universe, and it never stops, and it's in this pen, and then it's someplace else. It actually literally is someplace else, moving the atmosphere. It's someplace else. All right. So, and then moving the atmosphere moves other pieces of the, it just keeps going. It doesn't ever stops going somewhere. All right. So I would say it's so simple. And it's just unfortunate they made such a mess out of physics, because it can be understood as just being there's bits of force and they travel in straight lines like rays of light, like rays of magnetism, like rays of things. The little bits have a trajectory. So as the background image indicates, that's all there is. And that's the energy in the universe. And there's only a certain number of them, okay? And the idea is there's two kinds of matter, electrons and protons. And so it doesn't really matter. We could just call them matter bits. And the fact that they have charge is a complication, but it's not that complicated, but I'm not going to waste time with it here. And the simple truth is these bits stick to the matter. And when they stick to the matter, the bits go from going very fast, so having a very high velocity, to being slowed down. So I've used the analogy of Sisyphus, some guy rolling a boulder. And yeah, the guy could walk somewhere really quick, but if he has to roll the boulder, it's going to take up hours to get there. So the proton and the electron are pushed by collecting these pushers. And they can collect 1 or 2 or 5 or 10 or 20 or a million, whatever. And they'll go faster and faster depending on how many people are pushing, how many bits of force they've collected in a direction, okay, because they're in a disproportion. That is, they're in a place where more stuff is hitting from one side than it's hitting from the other side, just like gravity. And so they collect this stuff while they're in that differential. So while you're in gravity falling, you're collecting the differential based on 9.8 meters per second, per 1 second, a change in your velocity. That's how much velocity. You only get that much each time, or each unit of time. So you travel 4 times the distance, but you travel 4 times the distance in twice the time. So you only get 2 units of this pusher. If you had 2 units, if you got 2 pushers per second, after 2 seconds you only have 4 pushers. And after 3 seconds you have 6 pushers. That's all you have. Just as Newton stated, twice the force, twice the velocity. 3 times the force, 3 times the velocity. Their theory, their energy theory says, no, it's quadratically increasing. So twice the velocity, 4 times the energy, 4 times the force, you need 4 times the fuel. 3 times the velocity, you need 9 times the fuel. And you'll produce 9 times the force somehow. 4 is 16, 5 is 25. So obviously that's their theory. That you're supposed to be foolish enough to believe that it takes 25 times the fuel to go 5 times as fast. And they think you're dumb enough. And you are, apparently. I didn't think you would be dumb enough. Once I explained to you that's what their theory actually says, that you would say, oh, okay, I get it. That's obviously not a correct theory. It obviously doesn't take 25 times the fuel to go 5 times as fast. It's just absolute nonsense. 8-pound bowling balls going 16 miles an hour do not knock down more pins than 16-pound balls going 8. It's just, they don't. It doesn't happen. You're not stupid enough to believe it. I would have thought. But you are. Anyway, so the simple truth is that all you can do with this energy stuff, it's only in 2 states. So it's either flying free, going the speed of light, or it's stuck to a piece of matter going some lesser speed. That's it. That's the only 2 states the energy in the universe can be in. And all really that's happening is every time 2 big objects bang into each other, their atoms and electrons and protons all have a certain amount of energy, a certain state they're in. That's why they're moving in a direction, is they've collected a state. And they just start sharing the state and equalizing the state, so they're all in the same state. But there's no increase or decrease in the actual pushers. They're just going to say, I have 3, you have 1. I'll give you 1. I have 2, and you have 2. So just convert it into some kind of equality if they have enough time to exchange their conditions. If they don't have enough time, then they'll only do a partial exchange, like just rubbing against the surface or something. But that's all that's going to happen. You take motion that's in one place, and you just move it into another object. So you can move it from an elephant to a tree, or you can move it from a piece of chemistry. You can move it from take a a clump of something and cause a chemical reaction inside of it, and it'll produce heat, radiation, which is a bunch of jittering, vibrations, and the vibrations will be absorbed by the energy field and dissipated. Yeah, it's probably good enough. So energy is a real thing. Quantity of motion was actually, although that sounds kind of awkward, that's what Newton called it. It sounds kind of awkward. It's actually a really good statement because it is a quantity of stuff that moves. And you really do have to collect it. You really do have to get it from somewhere. The Earth is orbiting the sun. It didn't just do it. Okay? Something had to have velocity to keep hitting the Earth in one direction more than it got hit in the other direction. So in the messy, cloudy, clumpy, early solar system, there just happened to be more stuff going this way than stuff going that way, and this way won in the end. So when it all cleared up, because it all got gravitationally absorbed into bigger and bigger pieces of matter, the end result was there just happened to be more motion going one way than going another way. All right. I think that's it. And the Earth had to be at the right velocity to stay in a sustainable orbit. That was a evolutionary thing. Survival of the fittest matter. The matter that wasn't fit didn't last very long. That didn't have the right velocity to not be sucked in by the sun. All right. So, that's probably... It's really no more complicated than that, so I really shouldn't have to say much more. Energy is a real thing, a real phenomenon. It's not a mysterious thing. It's not woo forces. It's a push-averse. The energy has to actually contact something, move into it, push something real. So the energy, the photons, are real bits of momentum. They give their momentum to other things by sharing it. That is, they're very small. They have a lot of high velocity. They are absorbed, don't change the mass very much, but increase the velocity of the thing they stick to. So they put the energy in what we call a different form, but it's really the same stuff. Okay, it's just pushing big stuff versus pushing little stuff. Yeah, I think that's enough. I think so. We'll go with that. Alright, so let's play the video.
Why save energy if physics says energy is conserved anyway? Did Einstein...
Okay, so physics says it's conserved, but we know it doesn't conserve at all. Their physics says the bullet leaves the gun with 2,000 joules. The recoil of the gun is only 2 joules. So they violate Newton's third law. They don't care. The consequence of their theory is that you could put 2 light bullets in a gun, a zip gun that can shoot out both sides. You could put 2 light bullets in, and you could get from the same explosion 1,000 times more energy than you're going to get if you put heavy bullets in. 1,000 times. Merely because of this squared velocity function where mass is meaningless and velocity is everything. So by that theory, you're going to end up with saying, if I was to use the motion of the objects getting pushed by the pressure of the explosion out of the gun, I would conclude the energy is 2 entirely different numbers depending on what size bullet I use to test. So obviously it doesn't conserve. It doesn't make any sense. Their theory is that I have, a 5-ton train going 10 miles an hour, and I add 5 tons to it, and I magically lose half the energy. Where's the conservation? And it's magically lost. They'll say something got deformed, but they won't show you any bent fenders. They won't show you anything deformed. They won't show you anything flying into space. They won't show you any thermometers. They won't show you anything to indicate half the energy actually went somewhere. Because it didn't. Because all of the momentum was conserved. So it's just nonsense. Kinetic energy is having an energy duality. The photon thing you can almost understand because it's visually, it preys on your intuitions. Oh yes, it looks like. But this doesn't even look like. There actually is nothing that looks like quadratic increases in energy, except maybe the bullet gun example, where the bullet seems like it does so much more damage, but it only moves a very small amount of matter. It just happens to move it very, very quickly and dramatically in a small area. So it looks like more energy, but it isn't. So I guess there are some examples where you could be fooled. But it's just a fact that the guns on the ship shooting cannon, right? The ship is recoiling. You know, they had to account for all that. They had to put the cannons on wheels, and they had to account for the fact that the ship is actually going to be moved by the cannon fire. It's like they couldn't shoot cannons off just one side of the ship without shooting other cannons just to keep the ship from wobbling too much.
Really say that energy is not conserved? And what does energy have to do with time?
So did Einstein say that energy isn't actually conserved? Now, when they say Einstein said, they're saying it's what they extrapolate into Einstein's mouth. So Einstein didn't invent gravitational waves. He didn't do a lot of things that they blame him for. Einstein's opinion of a Einstein ring, that they named after him, was you would never see one because it's mechanically impossible, because you can't collect the photons because the gravity lens is exactly the wrong shape. I mean, it's exactly wrong. It's wrong, dramatically wrong, in terms of it's not a light collector. It's just they have so much wrong.
This is what we will talk about today. I looked up energy in the Encyclopedia Britannica and...
Yeah, well, you could just go to Wikipedia. But anyway, yes, and I've done all that. So I have a bunch of videos dissecting the nonsense in the Wikipedia pages. And the true story is the word energy wasn't used in Newton's time. And so now we're just trying to find a replacement. So we have two choices in the time of Newton. There was a thing called the vis viva, the living force, proposed only by Leibniz and suggested by Huygens. But Huygens never aggressively defended it. And the Newtonian idea that no, momentum runs the universe. So they didn't use the word momentum, okay? It was called quantity of motion. But it was the same thing, mass times velocity. So the two competing theories were energy is mv or mv squared. And they never compiled any evidence to prove one or the other. And the French in the 1700s, early 1700s, had a contest kind of pleading with physics. Could you please resolve this? And they couldn't produce any resolution because nobody had any experimental evidence. It's just a simple fact. Nobody could show a video of it. So even if they showed you a lever and showed you, one mass moving 4 times the velocity equals a 4 mass moving 1 velocity. That it's just not true that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet, which Leibniz said, the defender of mv squared. He said it. He didn't prove it. Okay, and it won't be the same impact. You need to take, and one velocity is one mass needs to move 4 times the velocity to have the same power or capacity to do work as a 4 pounds moving 1 velocity. Momentum is conserved. Momentum is what all of the Newton's laws were written about. Those laws weren't written about mv squared. They were written about momentum. Newton thought the energy of the cannonball was the same as the energy of the cannon. And they don't think so. They think the cannonball has 500 or 1,000 times more energy. It's just the truth. That's their Bible. Now, if they want to run away from their Bible, that's fine. But that's what their Bible says.
It told me that energy is the capacity for doing work, which brings up the question, what is...
Yeah, so the capacity doesn't mean it's exclusive. It means that you can do work with energy. Okay, that's a reasonable statement. But energy is energy. There's no other way to describe it except it's motion in the universe, and that's the simplest way to describe it. Energy is motion. Anything that's moving is going to have energy, and it has to be a thing. So as long as you believe the universe is made out of things, then you don't have a problem. Even if there's a force, if you believe the force is a thing with properties, no problem. Whenever the property is you're moving, that means you have the capacity to share your motion. And even if you're not moving, you're going to share your condition of not moving if you're involved in an interaction with something else that must obviously, it can't hit you. If you're not moving, something that is moving has to hit you. So there's going to be an exchange of motion. So energy is the event, let's just say, of seeing an exchange take place. An event where energy is exchanged, where motion is exchanged, let's just put it that way. Where motion is exchanged, energy is apparent.
Work. The encyclopedia says work is a measure of energy transfer. That seems a little circular. And
no, it seems just fine, frankly. That's when we acknowledge its existence. The fact that it exists even when it doesn't hit something is the reality, right? So there's lots of photons that fly out of galaxies and they don't hit anything, right? They travel billions of light years and they can still hit you because they didn't hit anything else. And they could have missed you and then still be traveling another, billions and billions of light years. So that energy seems benign, but it doesn't mean it doesn't exist.
as if that wasn't enough, the encyclopedia goes on to say, well, actually, not all types of energy do work. And also...
So, yes, work is just a word we've used to describe stuff we like and, motion we like. And the motion we don't like, we call waste or, heat. We put in some other category. And it's not really that it's not energy. It's just hard to do anything with it. It's not that you can't do anything with it, that you can't collect it and put it in a battery. We could take every circumstance where heat is a byproduct, and we could collect it. It's just that it's expensive to collect it.
Energy is always associated with motion, which actually it is not, because E equals mc squared.
So that's the silly part. She's telling us E equals mc squared because Einstein said so. And it's sort of just made up numbers, frankly. I mean, there's no proof of this one either. That the actual every little quantum of space, contains every Planck constant of space contains this particular amount of pressure or capacity to move, or stuff moving through it, or however the diagram would be. But I would make the obvious argument that masses don't have any energy. Forces do. Okay, and that's it. Force bits moving the speed of light. They are collected as a quantity of motion, just like you would collect money. So the force has all the money, and the matter tries to steal some of it, collect some of it.
I hope you are sufficiently confused now to hear how to make sense of this.
Okay, there's nothing to make sense of. If you pay any attention to the history, you realize there was no evidence provided, and they just jumped to these silly conclusions, and there was just no good reason to believe it made any sense at all to square a velocity. It doesn't geometrically make any sense, and there was no physical evidence demonstrating it to be true.
Illustration for energy conservation is a roller coaster. At the starting
So again, this is bullshit, in the sense that there's no literal the energy is always in thing, okay? And all you're doing is putting something in positions, and you're limiting where it can fall and how far it can fall in gravity, and you're taking the energy away and giving the energy back, but it's not it doesn't move into some category that's reasonably described as potential and actual. It's always actual river. So a better analogy would be a river and a boat. And the fact is you can have a boat, okay, and you can give it a certain velocity upstream, and then you can let it fall downstream, and then let it bounce off a rock, and then move around, and it can keep, it can move in and out of that force, just sideways. Let's see if I have to add a force pushing you back up, so it has to be a lot of rocks you bounce off of. So I have to turn you into a rubber ball or something. But anyway, the point is the car starts, and you're just saying, okay, there's a river, and now I'm going to untie the boat. I'm going to disconnect it from the river bank and let it fall in the water, let the water fall, the stream. And the current's going to carry it, all right? And then I'm going to force it, okay, to go against that river. And, this is all this is just using the motion to fight the gravity. So when it goes down, it gains a high velocity, plenty of velocity to go all the way back up again. So you only go up a little bit, so you take away a little bit of its velocity, and now you give it an opportunity to fall again, and that's all you're doing. So if there was no friction, it would just go around and around forever and ever because of the initial motion you gave it. And that's it. And that's how it really does work in the universe. That you could theoretically poke something in space, like a blob of water in the space station or something. You could poke it, and it would just continue to jiggle, once you started it. If you take away the atmosphere and it's just in space, weightless, undisturbed, even if you give it an orbital velocity, and you can't lose its jitter.
Point, it has only potential energy that comes from gravity. As it rolls down, the gravitational potential energy is converted into kinetic energy.
So this was just graphics fun, I imagine, where they created this ability to superimpose her inside of this with the green screen. Blah, blah, blah. So I wonder how much work that was for the gimmick.
Meaning that the roller coaster speeds up. At the lowest point, it moves the fastest. And as it climbs up again, it slows down because the kinetic energy is converted back into potential energy.
So again, there's no kinetic energy, there's momentum. She could have just said momentum and it would have been perfectly valid. So, but they don't do that, okay, because they're selling this alternative polyester version, and it's just bullshit. Let's see, and what else is there to point? Well, there's 4 wheels on this little cart too. You got to count the amount of energy caught up in the angular momentum. But anyway, so there's no real thing of potential. The fact is that if I get the cart all the way back up to this height, it has 0. Okay, again, real motion in the sense of the imbalance. It's lost all of its imbalance, and it has to regain it again by falling in the gravity. So it's like, you have to get it, you give it back to gravity, takes it away, and then gravity gives it back, and gravity takes it away, and gravity gives it back. But there's nothing really called potential. You're not storing potential in it. It itself doesn't have anything. The boat sitting on the side of the Mississippi River isn't legitimately described as something with a bunch of potential, because it doesn't have anything. It's not doing anything. It doesn't have anything until you put it in the active stream, and the active stream gives it something. And that's what gravity's doing. It's an active stream constantly pushing on us, and if we're not stuck on the earth, or we're not bound by friction, it'll push us 9.8 meters of velocity per second. Fact. All right, just a little factoid to throw in. So the trick with gravity is that it's moving the speed of light. So your motion of going from 10 miles an hour, let's just say 10 meters per second, then you go to 20 meters per second, then 30 meters per second, then 40 meters per second. Those are tiny increases relative to the speed of light. So you can understand that, yes, there would be a point where you're going so fast that the force can't push you, because the force isn't going fast enough more than you. So it's as if, okay, you have so many Sisyphuses that more Sisyphuses aren't in the field to fill you in, to push you again. They can't even catch up to you, so to speak. You're moving so fast that you're almost outrunning the Sisyphuses. So obviously that doesn't even become even close to an issue until you're going hundreds of thousands of miles an hour.
neglect friction, energy conservation means the roller coaster should have just exactly the right total energy to climb back up to the top where it started.
Yeah, well, we know it does. It's just that the friction takes it away, so it does theoretically conserve. The energy never goes away. It never disappears. So if you don't let it leak out, if you keep the energy in the car, the motion, the momentum, and you just keep making little exchanges, but you always get back what you put in, yeah, it theoretically goes forever because the energy never dies. Just as Descartes kind of pointed out 350 years ago, is that there's every appearance that that's how the universe works, that the same energy moved the dinosaurs as moving you, that the energy never goes away, just like the matter never goes away. The matter I'm made out of was somewhere 100 years ago. It was somewhere 10,000 years ago. It was somewhere, the molecules, 1 billion years ago. Just a fact. Okay? It's all got a history. And the history has to include the Sisyphuses and the boulders. The boulders are indestructible. The Sisyphuses are indestructible. And you're just saying, what are they doing today? Because today will look different than yesterday. But it's the same amount of actual players playing out the parts.
In reality, of course, friction cannot be neglected. This means the roller coaster loses some energy into heating the rails or creating wind. But this energy is not destroyed. It is just no longer useful.
So that's the point. Is it's certainly collectible is the point. So it is that it's not useful. It's not economically viable to collect it, charge batteries with it to lift the cart up the roller coaster. But that could be done. You could take all of the energy from the friction, convert it into electricity, convert it and give the cart an elevated boost, compensating for what it lost to the friction. So each run around, it's lost a certain amount of friction, 15% or whatever, 20% maybe. And you could collect all of it and just give it a 20% increase in its velocity, and then it goes forever.
To move the roller coaster. This simple example tells us two things right away. First, there are different types of energy, and
so there's no different types elementally. Everything, there's only one universe. It's made of that stuff with matter bits in it, electrons and protons. So it's black space, bits of force, and bits of matter, and that's it. That's the elemental universe. That's the only real universe. We're just big giant clumps of that.
They can be converted into each other. What is conserved is only the total of these energies.
So what's conserved is the momentum. So if you recognize that the photon is not a massless particle, okay, they actually carries momentum. So it has a very small mass and a very standard speed. And the fact is that works. That's what Einstein actually got the Nobel Prize for, which was explaining that basically photons are clumpy, and it's clumpy energy in discrete little tiny bits. And it's just ironic, okay, that his other theory was so wacky and silly.
Second, some types of energy are more, others less useful too.
So again, useful is the bullshit word here. There's, useful to who? So that's like saying saucers for teacups are to some people quite useless. I never used one. So yeah, useful is depends on how fancy you are. Okay, whether you worry about such crap. But otherwise, the fact is it is all real and stuff to account for. So no matter how the energy, no matter how discreetly and small the little bits of energy, the dust, you could argue it's like the sawdust coming off a saw or something, and you could think of that as the loss to friction, is the little pieces flying off, and somebody could care and vacuum them all up and collect them, or somebody could not give a shit and just say, fuck it, I don't, not interested.
Move things around. But what really is this energy we are talking about?
It's motion of mass. That's it. So if it's not, it doesn't have any mass, then it's not in the universe, frankly. And if it's not moving, okay, that means it's not going to hit anything. So something has to hit it. So it won't be the carrier of an interaction. But it's going to be just the same. It's going to be in interactions. It really doesn't matter if, your car crashes into his car at 60 miles an hour, or his car crashes into your car at 60 miles an hour. It doesn't really make a difference unless your car is way different. But I'm just saying, it's a practical matter. It doesn't matter whether you moved or he moved. The fact is the exchange is going to be the same damn thing.
There was indeed a lot of confusion about this among physicists in the 19th century, but it was cleared up beautifully.
Oh, it wasn't cleared up beautifully by Einstein. I'm sorry, it was covered up. It was ruined up.
By Emmy Noether.
Oh, Noether. Okay. So this is another part of physics where you just say, what is this they're talking about? Because I can't still, to this day, can't make any sense out of this nonsense where somehow she proved conservation. You don't need a proof. What you need is a piece of evidence indicating a real loss somewhere where energy actually was destroyed, and that they don't have.
1915. Noether proved that if you have a system whose equations do not change in time, then this system...
So whatever that means, a system whose equations don't change in time. What does that even mean? I don't even understand how a system, like what's the equation where mass and velocity don't change? I mean, it's, the size of the space doesn't change. I mean, what are you talking about? What is the changeable thing? Well, anyway, it doesn't matter.
Has a conserved quantity. Physicists would say such a system has time translation invariance.
So that does sound like bullshit, right? So this is supposed to be physics without the gobbledygook. I just don't know how you get more gobbledygook than that. How the fuck do you actually say something gobbledygooker than that?
Energy is then by definition the quantity that is conserved in a system with...
This doesn't make any sense. By definition, by her definition, but I'm just saying that's what already Descartes basically said is, look, it's conserved. There's no place to generate energy and there's no place to destroy energy. That we can observe, and it has every appearance that, what goes in comes back out, eventually.
Time translation invariance. What does this mean?
Time translation invariance. Blah blah, gibble gibble, blah 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 blah, gobble gobble.
Time translation invariance does not mean the system itself does not change in time, even if...
She just said it. That's... You're supposed to be doing a system that doesn't change with time. That's what you said the condition was.
If the equations do not change in time, the solutions to these equations, which are...
Whatever that even means. These solutions to the equations, right? So that means another equation is somehow the solution to the equation is some other equation. They never actually solve the equation, come up with the number 5. No, they just keep deriving the equation, turning it and turning it, and turning it and twisting it and twisting it, and that's all they have is twisted equations. They don't actually solve any equations.
What describe the system usually will depend on time. Time translation invariance just...
It's just so silly. I mean, so obviously in this case, time is really important in understanding how you can communicate how an interaction happens. And so the simple truth is, if the interaction happens too quickly, you can break this glass with almost no energy. A tiny amount of energy will break it because it's translating, okay? It's interacting too fast for the matter to spread the energy. Too many sisyphuses are going through the little material doors and they're pushing stuff way too fast, and the way too fast motion is going to crack it and shatter it. But if you give it time to accept the sisyphuses, they go through the door one at a time, blah, 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 then it can accept millions of sisyphuses. But it can't do it if you try to cram them all into one house. Then they just explode the house. So the sisyphuses have to be able to spread. And the spreading rate is like the speed of sound in the material. And as soon as you start going faster than the speed of sound in the material, as soon as you start trying to push force through something faster than that, you start breaking down all the fences and the doors and eventually all the houses.
Means that the change of the system depends only on the amount of time that passed since you started an experiment. But you could have...
So how could this, I mean, this is just so abstract. It's like, what are you talking about? Since I started an experiment? What experiment? What are you talking about?
Started it at any moment and gotten the same result.
Yes, this is just basically saying the laws of the universe aren't variant. They're always the same. So the rate of gravity is the same. All the basic functions. The mass of electrons is the same. The mass of the proton is the same. So these elemental features, properties, don't change. They're not variant. Obviously, that means that the motion can be conserved because there's no thing to lose it to. There's no friction for electrons and protons.
Whether you fall off a roof at noon or at midnight, it will take the same time for you to hit the ground.
It's just like you're saying, what, somebody had to prove that? I mean, it's just so, why would anybody even doubt whether the rate of gravitational acceleration changes when the sun's out and when the moon's out? I mean, obviously it does subtly. I mean, it's just a simple fact that, which side of the Earth the sun happens to be at on a particular point does change. I mean, the tides prove it. So, I mean, it's kind of obvious that the sun and the moon are affecting, okay? But it's not going to make a radical, a change you're going to detect.
Oh, that's what time translation invariance means.
It doesn't mean nothing. So that was a big waste of time, right? Because nobody really believed that the laws of physics change because it's, the sun's out.
So energy is conserved by definition. And
so she says it again, by definition. By whose definition? And what do you mean by energy? Momentum is conserved. By the definition of Newton's third law, it's conserved. If I have $20 and I give somebody 10, I lose 10. I don't need an opposite reaction, right? I mean, it's just that I'll be in the opposite condition. So it's probably a better law to write, for every action, okay, there's an exchange of condition. And that's what's going to happen. You can't make that without making that.
Noether's theorem gives you a
somewhere.
Concrete mathematical procedure.
Oh, so again, a mathematical procedure to figure out that the basic laws of physics are invariant, not invariant, not variant.
To derive what energy is.
Oh, amazing. Just amazing. And again, when she says energy, she means this mv squared crap. That somehow velocity is much more important than mass. And no, they're equal players in defining the circumstance. And how else to describe that? And it all has to do with the fact that the force is very tiny and discrete, a million times smaller, but it's going a million times faster, so to speak, than the matter. And so when the force connects to the matter, it has a huge velocity to work with. So even though it's tiny, the amount of extra velocity it can give is huge to balance. So the little tiny increase in its mass comes with this huge increase in potential velocity.
Okay, I admit it's a little more complicated because
it's a lot gobbledygook-y.
Because if you have some quantity that is conserved, then any function of that quantity is...
So any function of the quantity. I mean, this whole rhetoric is, she wrote a book called Lost in Math. And you're just saying, man, you are still so on a road to nowhere. I mean, you are so still without a clue where the map is.
also conserved. The missing ingredient is that energy times time has to have the dimension of Planck's constant.
So energy times time, again, how can it make any sense when time is already in the velocity? The velocity is already measured in time. It's already in there.
Basically, it has to have the right units.
Okay, so this is basically it has to have your units. So you think there's such a thing as a squared second. That's somehow a rational, perceivable, geometric substance. Now, a meter, you can understand a length, and I could apply the length to a width. All of that makes sense. Sure, I can get that. A square second? How the fuck? A square velocity? How can I do that? How can I square a velocity?
I know this sounds rather abstract.
Yes, that's right. Just absolute nonsense. 300 years of crap. And you didn't illustrate that again, just take it for what she's offered. She's offered this silly roller coaster example that she could have used the word momentum and it would have been just as good an explanation. Momentum is energy. And they won't find an example where momentum doesn't always work. Momentum landed us on the moon. So again, will she admit it? Will this scoundrel just fucking admit that she knows damn well that momentum of the thrust used to navigate the lunar module is what successfully landed it on the moon. If they had calculated the kinetic energy of the thrust and expected the lunar module to equally and oppositely react, they would have crashed on the moon. That's a fact. And she knows it's the truth. So why this bullshit? Why this kinetic energy fraud? It's always been momentum. It always will be momentum. The universe runs on momentum. Nothing else. It's the only fuel there is.
And mathematical. But the relevant point is just that physicists have a way to define what energy is, and it's by definition conserved.
Just keep saying this. We've decided it's conserved. Now, we're not going to give you the reasoning for why we think it's conserved. But obviously the reasoning is it's a bowling pin argument, right? I mean, you can follow it. The bowling ball hits the pin flies off, the pin hits the wood, dents the wood, does this, does that, creates some heat, vibration, sound. We can figure it all out, and we can follow each little element. It's just, our physics can do that.
Which means it does not change in time. If you look at a simple example, for example that roller coaster, then the conserved energy is as usual the kinetic energy plus the potential.
So more nonsense of this potential energy and kinetic energy. And again, that theory has in it some notion, that I could crash, a 10-ton train into a 10-ton train and have no energy, because they went off in the opposite directions. So if they bend fenders and crush, inelastically, I know I can see all of the energy and I can see where it's going. But if they elastically bounce off of each other, I'm supposed to say that was a non-energy event. There's no energy in the universe. There's the same exact energy. You have something going this way and you have something going that way. Nothing canceled. There is no cancellation. They either crush something, break something, smash something, make noises, or they just repel with exactly what they started with.
Energy. And if you add air molecules and the rails to the system, then their temperature would also add to the total, and so on. But if you look at the system with many small constituents...
So we know that temperature is something we can collect. She's saying temperature is completely in some way uncollectible, when no, we could collect it. We just don't want to spend the money to do that.
Like air, then you will find that not all configurations of such a system are equally good at causing a macroscopic change.
So whatever this mush will mean. So she's trying to wiggle a room in here somewhere to say something can be lost. No, it can't be.
Even if they have the same energy. A typical example would be setting fire to coal.
So there's nothing about this example that is, where we could scrutinize it, because we're talking about trillions of molecules, and we're talking about the energy basically stored in the compression of nucleuses. And now we're going to, expand the nucleuses by doing some chemical reactions, and put them in ionized and deionized states, and change them in do all kinds of exchanges. And the fact that those exchanges mean there's lots of motion, because like magnets, I could stack a bunch of magnets, and then if I had a little stick tied to one of them and I turn that one really quick, then all the other magnets fly off because I've changed the balance.
The chemical bonds of the coal molecules store a lot of energy. If you set fire to it, this causes a chain.
So it doesn't store the energy in any other form than the energy in the nucleus, the arrangement of the nucleus. So the more arranged the nucleus is, the more capacity it is to fly apart. So it's the strong force argument. There's no strong force. What there is proton and proton, and they can see each other and they repel. And I can stick an electron between them, and now I can get the protons really close together. But if I create a circumstance where now this electron gets kicked out, I have this huge potential for the protons to fly apart. So that's what you're doing when you create some kind of thermoenergetic chemical process, is that you're basically just saying you're taking a bunch of these nicely arranged stable conditions, and you're going to create an unstable condition.
Reaction between the coal and the oxygen in the air. In this reaction, energy from the chemical bonds is converted into kinetic energy of air molecules.
So it is not kinetic energy, it's just momentum. The molecules are being moved, it's momentum, it's a mass and a velocity. The water in the air, the nitrogen, the hydrogen, all of it has momentum. It doesn't have kinetic energy. It's not mv squared, it's just mv.
This just means the air is warm, and since it's warm...
So, see, by their theory, they've taken something, that is a clump, a big hunk of mass, and they've converted into a bunch of little masses moving quickly. And their calculations are that somehow they've increased the energy, because now they have a bunch of little things moving quickly. Lots of v squares. But they really haven't done that. It's not the truth. The truth is that's the same momentum was in the coal that you've put into the air now. It's the same number of sisyphuses pushing matter. It's just they're pushing them in a more chaotic way. In the coal, the sisyphuses were organized in nice little circles. In the oxidized hydrocarbons, you no longer have nice organization, and so now you have a bunch of sisyphuses flying free and a bunch of matter bits flying in directions that aren't attached to the coal anymore.
Warm, it will rise. You can use this rising air to drive a turbine, which you can then use.
So of course you wouldn't use rising air, so I don't even know why she says that. It's not the buoyancy of the byproducts of burning the coal. It's not the fact that the heat rises that you're going to collect. You're going to collect the expansion. The point is the atmospheric stuff expands in size by 1,000 times. So you have 1,000 times increase in the size of the atomic pressure of the atoms. The atoms are bigger.
Used to say move a vehicle or feed it into the grid to create electricity. But suppose you don't do anything with this energy, you just sit there and burn coal. This does not...
So again, the reason why they use water for steam is because, when you take the water, it has this much volume at 50 degrees, and that at 200 degrees, its volume is, literally 1,000 times bigger in terms of its capacity to overcome atmospheric pressure. So at the same atmospheric pressure, it takes up a much larger space because it has more energy. more motion. It's not trapped in circles.
Change anything about the total energy in the system because that is conserved. The chemical energy of the coal is converted into kinetic energy of air molecules, which...
So again, she keeps saying kinetic energy, and we know that the kinetic energy cheats. Okay, the rocket and the thrust. So the rocket thrust, if I calculate its kinetic energy, and then I calculate the kinetic energy of the rocket moving, the two won't match at all. There'll be 1,000 times difference in the two numbers I get. The thrust is going to have a huge number, and the rocket's going to have a very small, 1,000 times smaller number. But if I calculate the momentum of the thrust, and then calculate the momentum of the rocket, yes, I get Newton's perfect symmetry. I get the same amount of momentum going both ways. That's obvious. It's that obvious how wrong what they're saying is. One theory works perfectly, the other theory creates nonsense and violates the third law.
Distributes into the atmosphere, same total energy. But now the energy is useless. You can no longer...
So she just called it useless. We know it's not useless. We know heat is really easy to... I mean, you can do it now with thermocouples. You can just, create a thermocouple, have it just sit here. Your event is going to happen on this side. Your event will hit this side. This side will be hotter than that side, and that's going to create electricity. So we know we can collect it. It's just that we don't want to spend $4 million, to collect, the lost $3 of energy, from a stove. Kind of obviously.
Longer drive any turbine with it. What's the difference? The difference between the two cases is entropy. In the first...
So entropy is just another fake concept that energy tends to go in a direction when we're taking advantage of the fact that the sun is doing exactly the opposite. The gravity is charging the battery that has the sun burning hot and feeding us with discrete heat that we are converting. So again, the idea that the small particles of heat aren't collectible is, again, that premise is broken by the very idea that we can make a solar panel and collect it. I mean, every time you're collecting electromagnetic radiation, in a way, you're collecting the heat of the universe.
Case, you have the energy packed into the coal and entropy is small. In the latter case, you have the energy distributed in the motion of air molecules, and in this case, the entropy is large.
Yeah, but it doesn't matter. Like, you just had them hit you in the head. You can collect them. You just got to wait for it. But you can absorb the energy back again. You just have to wait for them to bounce all over the place and finally come back to you again. So it could take time to get the energy back. And again, it's just expensive.
A system that has energy in a state of low entropy is one whose energy you can use to create macroscopic changes.
So again, you can use both, and it's just wrong to say we can't take advantage of the energy of the convection that transfers moisture to the upper atmosphere, and then also take advantage of the rain falling down. We can collect it on either part of the cycle.
For example, driving that turbine. Physicists call this useful energy free energy and say it does work.
All right, so the idea of free makes some sense in terms of unburdened pushing matter. So there's a difference between energy moving the speed of light, that is force, and the stuff not moving the speed of light because it's pushing matter. So I think that's an easy and reasonable distinction, but that's obviously not what they mean by free energy.
If the energy in the system is instead at high entropy, the energy is useless.
So again, in the entropy part comes again, you could say that you can create an explosion and you have energy going in all directions, and you just put it inside a container, and then you can collect it as an expansion in the container. So there's lots of ways to collect disorganized energy.
Physicists then call it heat, and heat cannot do work.
So that's silly. So we know that heat can do work, and we certainly know that it can collect, I mean, the idea that it can thermally move things, but more importantly, that whole idea of convection in so many ways that heat does work right in front of our eyes.
The important point is that while energy is conserved, free energy is not conserved.
So the idea that the force isn't conserved is what you just said there pretty much, and that's just nonsense. So there's no such thing as motion that doesn't have a history. So every event is made out of actions, and every action point has players, and every player has been somewhere 10 million years ago. Every one of the players was somewhere. The Siphicuses all have a 13 billion year old history, or whatever the age of the actual universe is, and so does the boulders.
So if someone says you should save energy by switching off the light, they really mean you should save free energy.
No. What the point would be is to say that, yes, it's all valuable in terms of this is what we live on. And we live on a lot of energy. We need a lot of energy because we're animated and moving. So we're obviously involved in doing a lot of exchanges, and the exchanges require there to be lots of available Siphicuses.
Because if you let the light on when you do not need it, you convert useful free energy from whatever is your source of electricity into useless heat that just warms the air in your room.
Right, so warming the air in your room is essential to your survival, frankly. So we know that that's hardly useless. So again, it just doesn't make any sense to call heat not a useful product, because we deliberately convert batteries into heat often for our pleasure, as if we wanted to do that work of heating the air so we don't freeze and die.
Okay, so now we have seen that the total energy is by definition conserved.
Okay, so again, by definition. There's got to be a better way to say it. I mean, again, Descartes said, here's the challenge. Give me a reason why it doesn't seem so. Show me something that says it isn't so. Show me, because it has every appearance that the energy always goes somewhere. You just take big energy and move it into little energy, and then you take little energy and put it back into big energy. Gravity restores the entropy. So the fact that energy gets dissipated from us and turns into thermal and radiant energy, well, that radiant energy is actually what's creating gravity.
But that free energy is not conserved. Now, what about the claim that Einstein actually told us energy is not conserved? That is correct. I know this sounds like a contradiction, but it's not. Here's why. Remember...
So it'd be nice to have actual quotes in context, because I really don't think Einstein was making any big argument about any substantial losses to the actual universe. But the idea, if the universe is expanding, obviously somebody would say, well, yes, it has to get colder because it has the same amount of energy in it. So in a sense, the temperature can't be conserved because you're expanding the space the temperature has to heat. So, I mean, in some sense, and you're changing the mv squared thing even. The E equals mc squared. You're even changing that if the universe is expanding. You're diluting, how much space the Siphicuses have to travel to get from work site to work site. So in total, over time, they have to do less work because you've made it longer to drive to work, kind of thing.
That energy is defined by Noether's theorem, which says that energy is that quantity which is conserved if the system has a time translation invariance, meaning it does not really matter just at which moment you start an experiment. But now remember that Einstein's theory of general relativity tells us that the universe expands. And if the universe expands, it
So tells us. I don't know if Einstein actually went for that crap. So again, it's just more, I don't know. I mean, do you really think that's what's happening? The universe is expanding? You know, did they really? They didn't think there was any possible explanation for red and blue shift except some silly notion that space keeps poofing into existence between everything all the time, and everything's getting further and further away from everything else. When there's a simpler explanation, which is the universe is still full of atoms, hydrogen atoms, that aren't going anywhere very fast, and they're in the space, okay, kind of just stuck in it, because the hydrogen atoms, unlike the helium nucleuses, the hydrogen atoms are dragged to a halt. Their electrons and protons can't keep going in space. So even if they had a velocity when they were shot into the space, they lose it and just end up stuck in slight gravitational fields and move kind of slowly. But anyway, it's full of it. And the fact is when the light hits a hydrogen atom, it's transparent, but it still does, okay, through Compton scattering, it does reduce the frequency of the light. So the simple explanation is the further away something is, it should be redshifted because the light probabilistically has hit hydrogen atoms and has lost a little bit of its frequency with each impact. That simple explanation that the light is in fact tired, okay, that it's had a rough trip, does work.
does matter when you start an experiment. An expanding universe is not time translation invariant, so Noether's theorem does not apply.
Right, because you break all the rules. If the universe is expanding and the force is actually in the universe and it is a substance, you've expanded the space the force is in, therefore the force has less heat. And if gravity is actually being created by a force, which I think is the only reasonable explanation, then obviously that force is going to diminish if I expand the space that the force is in, and the gravitational pressures will all reduce.
Now, strictly speaking, this does not mean that energy is not conserved in the expanding.
Yeah, so that's the funny part, right? Because if the actual energy is something, then it's the somethings haven't been destroyed. They're just requiring the somethings to travel more space. So they've lost more impact potential because they can't go to 5 stores if they only have time to go to 4. You know, they had the same amount of distance to travel. They could go to 4 stores. If I make the roads a mile longer, then they can't get to that 4th store anymore.
Universe, it means that energy cannot be defined. However, you can take the thing you called energy when you thought the universe did not expand.
So the thing you call energy, and that's the important point here. The thing is force, and the fact is matter can collect some force. And that's all there is. And you can't change how much of that's in the universe. But yes, if you're going to make the universe bigger, that force has to travel more distance to have interactions, so there'll be less interactions and less appearance of energy.
And ask what happens to it now that you know the universe does expand. And the answer is, well, it's just not conserved. A good example for the...
So, too silly. So this is what they've done. You know, I mean, Newton's third law is a really good piece of logic, and they're basically just said that to it. Oh, we don't, kinetic energy doesn't have to obey the rule. No. It's not a law for kinetic energy because that's special scalar fun. You can't make laws about scalar fun.
This is cosmological redshift. If you have light of a particular wave...
Oh, good. She brings it up. So, yeah, all you're really saying is look, the longer the distance the light travels, the more likely it has interactions. The fact is there's no theory that the interaction would blue shift the light. There's every possibility that with the interactions are going to redshift the light. They're going to expand the frequency. and the wavelength. And so it makes perfect sense. And, so yes, of course, light that's traveled 10 billion light years, I would expect it to be pretty fucked up.
Wavelength early in the universe, then the wavelength of this light will increase when the universe expands, because it's...
So it's just so silly to say that because, if you think that the photons, as Einstein said, right, she's not going to tell us about how Einstein said the light isn't made out of waves, it's discrete clumps. And you're going to expand the distance between the discrete clumps with magical poofed space. I mean, it's such a silly pile of shit.
Stretches. But the wavelength of light is inversely proportional to...
Awaken your inner goddess with Vitafusion's expertly crafted assortment of delicious and nutritious gummies.
Oh, and I brought cupcakes.
What is this?
Just use
Is Tide? If it's got to be clean, it's got to be Tide.
To the energy of the light. So if the wavelength of light increases with the expansion of the universe, then the energy decreases. Where does the energy go?
All right, so there's no decrease in the energy by changing the frequency. You're just changing the time over which the energy hits something, and it's cheating to say that you've actually reduced the energy. All you've done, because it's not fair to measure one piece of the universe in 1 second, because when you expanded the frequency, that means something moved away. All right, and the fact is when it moved away this way, it pushed in the other side of the universe. So the other side of the universe gained frequency. The frequency got smaller on the other side. So you can never lose the actual energy, because if you measure the 1 second on this side and then you measure the 1 second on this side, the two will add up to the same number. So you have 10, and yes, you can have 6 over here and 4 over here, or you could have 4 over here and 6 over there.
Oh, it goes nowhere. It is just not conserved. No, it really isn't. However,
so she keeps saying it. No, yes, it really is, and you're just fooling and deceiving people as if you have some evidence for this crap, which you don't.
You're
just talking a religious pile of shit.
Non-conservation of energy in Einstein's theory of general relativity is a really tiny effect that for all practical purposes...
No, well, it's not about practical, it's about the truth, and the truth is it's just crap. And it's based on a notion that somehow if you expand the balloon, the pressure, okay, no, that's probably the wrong way to say it, because to expand it, you have to put more air in it. If you have the same air and you make the balloon bigger, you really can't do that. Anyway, there's probably a better analogy. But yes, if you're making the space in which the stuff is in bigger, the pressure goes down.
Plays absolutely no role here on Earth. It is really something that becomes noticeable only if you look at the universe as a whole. So it is technically correct that...
So why would you even bring up a subject like that and call this something relevant to energy when it's some sort of, well, we can't see the effect and it's not measurable and it's not this and it's not that, but we'll just talk about that anyway. I mean, it's a terrible way to talk about energy conservation, frankly. Is to talk about this stuff that is not dependent on anything that can be proven or disproven.
Energy is not conserved in Einstein's theory of general relativity.
Says you again.
But this does not affect our earthly affairs. In summary, the total energy of a system is conserved as long as you can neglect the expansion of the universe.
So yes, and of course you can neglect that. I mean, you can believe that's a pile of crap. The universe isn't really, the space is not expanding. The space is not a thing. It's not a substance. It doesn't have any properties or capacity to do a goddamn thing. And the only thing that are players in the universe are the discrete bits of force and what we've already kind of figured out, the fundamental elemental particle called electron and proton.
However, the amount of useful energy, which is what
So again, bullshit terminology. All energy is useful. It's just some is more expensive.
physicists call free energy, is in general not conserved because
So again, saying it's not conserved when of course it is. The heat the Earth is radiating it onto other objects in space. And so they heat the Earth heats them. And so we're basically saying they push, the Earth gets pushed by the radiant energy from the rest of the universe, and the Earth makes its contribution to the pressure that compresses the universe.
of entropy increase. This video was
So there's no increase in entropy because the entropy engine is all created by gravity. Gravity consolidates objects, compresses them, and then they can expand. So you have to have gravity first, and then you can have expansion. But you can't have expansion and then gravity. That kind of thing. It is a chicken and egg kind of thing. But definitely the force has to initiate the action. The first mover.
sponsored by NordVPN, and
Oh yeah, so she's just, selling hackers. Learn how to be a lying scumbag hiding from rules and regulations. Be a culture destroyer. And they're pretending they're on the good side. This is like the old virus software, that would infect your computer. It's just so bad that people fall for this shit. These people are the people exactly out to hack the fuck out of you. And they're pretending, oh, they're going to protect me. Yeah, fuck you. Yeah, so funny. Anyway, till the next time and such, right? I think that's enough. We're a bit over time, actually, but, happens. So, I'll see what else I can find where she's talking about something elemental, that isn't complete, incomprehensible shit. All right. And, maybe we'll continue this. See how long we can roll the energy cycle. All right, till the next time and such, so forth and whatnot.